Hello and welcome to the webinar. My name is Francesco Ruffino and I am a principal HPC specialist solution architect in AWS. Today you will set up your first HPC cluster on AWS. And if you are already familiar with Parallel Cluster, we will dive deeper in some of the new features that we have made available recently. So here is the agenda for today. We will see why many customers are now running their HPC workload on AWS. Then we will talk about the tool that we will use today, that is Parallel Cluster, its architecture and how it works. Then we will run a quick demo to show how to install, configure, and run your first job on AWS. And at the end, we will have a Q&A session. Okay, so let's start with the why. Why many scientists and engineers are running their HPC workload on AWS? Well, Hyperion researchers ran a survey among the HPC users, and they have found that many of today's engineers, scientists, and researchers are constrained by their on-prem environment. With nearly 73% of HPC organizations reporting delayed or canceled jobs, this leads to a lot of unanswered questions and a loss in productivity. Moreover, with on-prem infrastructure, you can wait months, if not years, to procure new hardware. And this can leave HPC users with outdated hardware, and it can require a considerable time investment in creating and maintaining old technology. On AWS, on the contrary, your jobs can scale without any infrastructure limit. When you need to run a job, AWS will automatically provision for you the required computing nodes. And when the job is done, this will be automatically terminated, so you don't have to incur in any additional cost. Moreover, we continuously evolve our offering with the latest hardware type, so CPU from Intel and AMD, GPUs, FPGA, and so on. We have also developed Graviton, our own ARM-based CPU. So when a new instance type becomes available, you can immediately switch to the new hardware without having to wait for you to procure and deploy a new cluster. Finally, you no longer need to select only one hardware type for your HPC cluster, but you can mix and match different instance types based on the application requirements. Flying Whales is a French startup that is developing a 60 tons payload cargo airship for the heavy lift and outsized cargo market. The project was born to provide efficient and environmentally friendly transportation for collecting wood in remote areas. Initially, the company relied on an in-house high-performance computing cluster to perform their analysis. However, the cluster only had 200 cores, and the company didn't have the scalability or flexibility needed to support the workloads. Flying Whales chose to move its HPC environment to the cloud, running its CFD workloads on Amazon Web Services. Guillaume Martinat, the lead of aerodynamics engineers, reported that they can now run CFD workflows 15 times faster on AWS, thanks to the computing power and the internet networking performance they get using Amazon EC2. As a result, they can complete jobs in days instead of the months it's used to take. Moreover, using AWS Parallel Cluster, they can get jobs up and running in 15 minutes instead of taking months to acquire, configure, and manage servers. Another good example are the results obtained by the US Naval Research. In this case, we talk about weather simulation. As you know, this type of simulation is very difficult to accelerate because it hardly scales on a large number of nodes. Performance is strongly linked to the latency of the network that interconnects the compute nodes with each other. For this reason, we are very pleased that the results show how AWS is the fastest platform among those that have been tested by the customer. The graph represents how the wall time decreases as the number of processes increase. The red line is the results of a simulation made on AWS using C5N and EFA. Here I want to emphasize a couple of aspects. The first is that, as you can see, the red line is the one that provides the best performance, so the smaller wall time. In addition, the line stays flat longer than all the others, And this shows that on AWS, you can scale an MPI job across thousands of cores to achieve performance comparable to a supercomputer. Finally, when performing a weather forecast, you need to get the results within a given time frame. This is represented in the graph with the horizontal gray line. As you can see, using AWS, the customer was able to achieve these with fewer computing nodes and much earlier than all the other solutions. Okay, we have seen the why it makes sense to run HPC on AWS. Now let's see the how. So how you can use Parallel Cluster to easily deploy an HPC cluster on AWS. Okay, so what is Parallel Cluster? Parallel Cluster is an AWS-supported open source cluster management tool. And it is designed to make it easy for you to deploy and manage HPC cluster in the AWS cloud. It's an open source project, so you can find all the code in GitHub. Here I provide the link. And here you can also find the link to the documentation of Parallel Cluster. One of the most interesting aspects of Parallel Cluster is that it will automatically adjust the compute capacity based on the user needs. So what the user has to do is just to submit their jobs, and Parallel Cluster will receive the request, and it will automatically scale up and down the compute nodes, so the EC2 instances, based on the number of jobs and based on the requirement of each job. Then, once the job is completed, Parallel Cluster will automatically scale down and terminate the computing nodes that are no longer needed. Recently, we also have made available an important enhancement, that is the support for multiple queue and multiple instances. That means that now, from the Parallel Cluster head node, you can submit jobs using different instance type. So you can configure Parallel Cluster to use, as an example, C5N instances for if you want to use an Intel CPU, or you can use P4D instances if you're looking for an accelerated NVIDIA GPUs. And this is all available from the same head node. We'll see later how to configure this multiple queue, multiple instance aspect. There are other features that are very important. Parallel Cluster it's also an orchestrator that will deploy for you all the components that are relevant to create an HPC cluster and to run your simulation. So, for example, it will automatically configure for you the job schedulers. We'll see later the job schedulers that are currently supported. But it will also deploy and configure for you Amazon FSx for Lastre. FSx for Lastre is a managed Lastre file system that you can use as a Scratch area, for example. You know that Lastre is the file system that is most used in HPC at the moment. So it's very important to have the possibility to use it as a managed service. And Parallel Cluster will automatically orchestrate the deployment of Lastre for you, and it will automatically mount the file system on the computing nodes. Moreover, you can also use Elastic File System, or EFS, that is a managed NFS solution. This is useful to share, for example, the application or the home directories across the nodes or even across multiple clusters, because EFS can automatically scale across multiple availability zones. Parallel Cluster can also automatically deploy and configure Elastic Fabric Adapter, or EFA. EFA is a virtual network device that you can attach to your computing nodes to reduce the network latency and so to accelerate your MPI workloads. So it's very important to use EFA if you want to scale, if you need to run MPI jobs, and if you want to scale to hundreds or thousands of cores. Finally, Parallel Cluster can also automatically install for you NICE DCV on the head node. So NICE DCV is remote visualization protocol that is used to stream the graphics of your application from the cluster head node to your local client. Using DCV is very convenient because you no longer have to download the output from Parallel Cluster in order to visualize your results. You can keep all the data on AWS and just stream the graphics of the application from the head node to your local client without the need of downloading the output of your jobs. Okay, so now let's have a look at the Parallel Cluster architecture. Parallel Cluster is composed of 3 layers. So the first one is the Parallel Cluster client. You can install the client on your local laptop or on AWS using an EC2 instance or Cloud Shell or Cloud9. The only requirement for the client is Python and the AWS command line. We'll say that how to install it. Then you will need to prepare the Parallel Cluster configuration file. This is a very simple text file containing an high-level description of the HPC cluster that you want. We will see an example in a minute. Then you will use the Parallel Cluster command line to deploy the HPC head node on AWS. The Parallel Cluster command line will read your configuration file and it will transform it in a CloudFormation template. The template then will deploy all the AWS resources that you have requested. Once the deployment is done, you can log in to the head node using your SSH keys. From the head node, you can submit your HPC jobs using the standard job scheduler commands, such as sbatch, if you're using Slurm. Then Parallel Cluster will automatically deploy the compute nodes based on the number of nodes you need to run your simulation. And when the job is done, the computing nodes will be automatically terminated. As you can see in the picture, and as I said before, Parallel Cluster will also deploy DCV on the head node. So if you want, you can connect to the graphical interface, to the Linux desktop, using a DCV connection from your client to the head node. Okay, now let's have a look at the supported job scheduler. As I said before, Parallel Cluster can deploy different job schedulers for you. So currently we support these 4 different schedulers, and here in the table you see also the version that we are deploying at the moment. These are the Slurm Workload Manager, Son of Grid Engine or SGE, and the Torque Resource Manager or Torque. Moreover, AWS Parallel Cluster can also be configured to use AWS Batch, that is the AWS native job scheduler. Please note that starting on December 31, 2021, so the end of this year, AWS will no longer include SunGrid Engine and Torque support for all the released version of AWS Parallel Cluster. Previous version of AWS Parallel Cluster that support the SunGrid Engine and Torque will still be available for download and use. However, this version will not be eligible for future updates or troubleshooting support from the AWS service and the AWS support team. Moreover, the future release of Parallel Cluster made before and after the end of this year will not include support for either SunGrid Engine or Torque. So as I said before, starting from version 2.9, we have introduced the support for multiple queue mode and a new scaling architecture for the Slurm job scheduler. So the new scaling architecture is based on Slurm Cloud Scheduling Guide and the Power Saving plugin. So this is an important difference. For Torque and SunGrid Engine, Parallel Cluster implements the scaling capability by managing an auto-scaling group of the computing nodes. So that means that when you submit the job, if you're using Torque or SGE, the Parallel Cluster will increase the desired capacity in an auto-scaling group, and then the auto-scaling group will deploy the instances for you, and these instances will be automatically connected to the head node, so they will become part of the cluster, and your job will start to run. If you use Slurm, on the contrary, we will use the Slurm power saving plugin. So we no longer use the auto-scaling group. Using the power saving plugin is helping us to make the scaling faster in comparison to an auto-scaling group, because the plugin uses the run instance API to start the instances, and the run instances API can be faster in comparison to an auto-scaling group. Moreover, this API call will provide an all or nothing scaling. It means that all the instances you need to run your jobs will be deployed with a single API call. Okay, so we have seen the most important features. So now let's have a deep dive on the how-to, and let's see how to install Parallel Cluster. So in this section, we will see how to install the Parallel Cluster client, how to configure the client, and then finally how to use the client commands to deploy your first HPC cluster. So, as I said before, you can run the Parallel Cluster client on premises or on AWS. The Parallel Cluster client is distributed as a Python package and is installed using the Python Package Manager, or PIP. The supported operating system are Linux, Windows, and macOS, so basically everything. And as I said, the only requirement is to have a Python and the Python Package Manager installed, and also the AWS command line. It's also recommended to use virtualenv to isolate the tool and all its dependencies. We will see it in a minute. Okay, so let's start now the demo, and let's have a look at how the installation works. Okay, so this is my console. As you can see, I'm using Cloud9 for this webinar. The first command that I have run is to check the installation of PIP. Then in the second one, we have installed the virtualenv, and now I am activating the virtualenv. So I have the virtualenv active, and I can now install the application using the pip install AWS Parallel Cluster command. So, as you have seen, the installation of the Parallel Cluster command line is really fast. It will only take you a couple of minutes. The next section is the configuration of the HPC cluster. So if you have not created an SSH key for your AWS account, you have to create one using this command here. Don't forget to modify the permission, otherwise you will not be able to log into the cluster. Once you have your SSH key, you can use the Parallel Cluster configure command to start the configuration wizard. So the wizard will ask you a couple of questions and will automatically generate for you a configuration file. The wizard will ask you the AWS region where you want to deploy Parallel Cluster, the SSH key that you want to use, so you can use the one, for example, the one you have created before. Then the job scheduler that you want to automatically deploy in your cluster. So once again, you can choose between Son of Grid Engine, Torque, Slurm, and Batch. Then you have to select your operating system for the head node and the computing nodes. At the moment, we support Amazon Linux 1 and 2, CentOS 7 and 8, and Ubuntu 16 and 18. Then you need to select the minimum and maximum number of computing nodes. This is an interesting parameter. The maximum number of compute nodes define, as the name suggests, the maximum number of compute nodes. That means that if you try to run jobs that exceed this value, the jobs will stay in the queue until the other jobs have been completed. This parameter is important because basically will avoid you to incur in cost that you have not budget for. The minimum number is also important because once all the jobs are finished, the parallel cluster will move back to this number of compute nodes. You can have 0 as a minimum number, but if you want to have an higher number, that means that you will always have 1 to 10 computing nodes always up and running. Then you have to specify the instance type for the head node and for the compute nodes. And then finally, the wizard will ask you if you want to create a new VPC or if you will reuse an existing VPC. So if you want to reuse one that you already have, you have to specify the VPC ID. Otherwise, it will ask you what type of configuration, network configuration do you want. If you want, for example, 2 subnet, one public subnet for the head node, and the other one as private subnet for the compute nodes. Or if you want both the head nodes and the compute nodes to stay in a public subnet. If you want more information regarding the networking, you will find them at this link. Okay, then once the wizard is finished, you will be able to visualize the results, the configuration file in the .parallel cluster directory that is being created inside your home directory. And then you can create your first cluster using the command parallel cluster create name of the cluster. So in this case, webinar. And then the create command will automatically transform the configuration file in a CloudFormation template, and then it will deploy for you the CloudFormation template. And you can check from the command line or from the CloudFormation console the status of the deployment. Okay, we can now continue. So, of course, I have accelerated the demo just for the goal of this webinar. So it will take approximately 10-15 minutes to deploy the cluster. It really depends on the type of configuration that you have selected. You can control the status of this deployment using the parallel cluster command line and using the status command. So in this case, I'm asking about the status of the cluster that is called webinar, so the one that I have deployed before. And as you can see, parallel cluster will tell me that the creation is complete. So the cluster is now up and running, and I can use it. So parallel cluster will also tell me the IP address of the head node. So if you want, you can use your preferred SSH terminal to connect to the head node. Or you can use once again the parallel cluster command line. So the command to use is SSH. You specify the name of the cluster that you want to connect to, and then you specify the SSH key that you want to use. So in this example, I have specified the key that I have configured before. So you see now I am logging into the cluster. I am the user CentOS because I have decided to use to deploy with the CentOS 7 operating system, and I can immediately run the Slurm commands to start submitting a job. In this case, I'm running the sinfo. That is the Slurm command that show the status of the queue. As you can see, I have 1 queue at the moment, and as you can see, the number of nodes is 20. That is the maximum capacity that I have defined before. So what is important here is that you can then give basically the IP address and the keys. You can, of course, also add other keys into the configuration. And you can give access to your users. And then the users will be able to start submitting the job using the command is familiar with. So the torque or SGE or the Slurm commands. So from the user point of view, there is really no difference between running a job on-prem or running on parallel cluster. Okay, we have done the installation. Let's recap the commands we have seen before. Of course, we will share this slide deck, so you will have all the reference, all the links, and all the commands that I'm using in this example. The first command is to install the Python package manager in case you haven't installed it. Of course, the prerequisite is to install Python and the AWS command line. Then the second one will install virtualenv. With the third command, I have created a virtualenv. You can give the name you want. In my example, I use the HPC name. And then I have activated the environment. Then from this environment, from this virtual environment, you can start the installation using the standard Python package manager command. The name of the package is AWS-parallel cluster. Finally, when the installation is done, you can control if everything is fine using the parallel cluster version command that will return to you the version that you have just installed. Okay, now we can move to a more advanced configuration. We have seen in the wizard how to create a basic configuration. The wizard, as we have seen before, generates a configuration file, but we can edit this configuration file. We can create a configuration file from scratch. And within this configuration file, you can configure more fine-grained details like the network that you want to use, how to manage multiple queues and multiple EC2 instances, how to manage different pricing options, so using on-demand or using spot, and then finally how to configure EFA and FSX for Lastre. So we'll see all these, how to configure all these parameters in a minute. But before we jump into that, I would like to talk to you for a moment about how to choose the right EC2 instance for your HPC workload. So as you know, on AWS we have more than 400 different instance types. So it's good, I think, to have this variety of choices, but I think it can also be difficult to find the one that is right for your workloads. Well, one of the value is, of course, that you can experiment. So you can try different things until you find the one that really is good for you and match both your performance, but also the budget that you have available. But that being said, let me give you some guidance on how to, or some criteria that you can use to select your instances. So the first question that you can ask yourself is, can my application run on Graviton? So as you know, Graviton is an ARM-based CPU that has been developed by Amazon and that is now available on AWS. We have seen that C6G, these are the name of the Graviton instances, can provide very good price performance. Of course, not all the codes can. I mean, if you have the source code, you can always recompile the code using ARM. But if you don't have access to the source code, then you need to contact the ISV in order to verify if the application can run on ARM CPU. But if the answer is yes, then I really encourage you to at least to give a try to C6G and also C6GN. The difference between the two is that in C6GN you can also use EFA. We'll dive deeper on this in a minute. The second question is, does your application use GPUs or can benefit from GPUs? And then this can be split into other questions. Are you interested in doing rendering or graphic-intensive application, or do you need a GPUs for compute-intensive type of workloads? So for the rendering, the G4 family is probably the best choice. And here you have two options. We have the G4AD that is powered by AMD CPU and the GPUs, or we have the G4DN that is powered by the NVIDIA T4 GPUs. On the contrary, if you want to run compute, so here we have the P4D, for example, that is powered by the NVIDIA A100 GPUs that are very powerful. But there is also, for example, also the previous generation, the P3 instances that is powered by the Volta V100. These are still very powerful GPUs, so you can continue to use them if you want. And also the G4DN, we have seen customers using T4 instances also for their computational intense type of workload. Then the other component to take into consideration is, do you need a low network latency? So in other words, are you running an MPI job? So as you know, MPI jobs is really sensitive to network latency, especially if you want to scale to a very high number of nodes. So when we talk about several hundreds or thousands of cores, this is when the network latency can impact the performance. In order to reduce the network latency, we have this new network device available that is for free, and it's called EFA. And as we will see in a minute, you can automatically enable EFA in parallel cluster. But not all instances can be powered by EFA. So if you want to run an MPI job, I really recommend to have a look to the instances that can be powered by EFA, for example, C5N or M5ZN or the C6GN that we have mentioned before. Basically, all the instances with a small n at the end, these are the ones that are powered by EFA. Then the other question is, does your application benefit from very high CPU clock frequency? Because in this case, we have, for example, the Z1D instances that has been co-designed together with Intel. And in this case, the clock speed can go up to 4 GHz. But we also have recently announced that the M5ZN that can go up to 4.5 GHz. So in this case, this sounds like probably a very, very good choice if you're looking for a high clock CPU. We have recently published a white paper that will dive much deeper into how to optimize the HPC workload with the right choice of Amazon EC2 instances. So I highly recommend to download and read this white paper if you want more information. Another very important source of information is a new service that is called Amazon EC2 Instance Types. And is a service that is available from the console. So you see here from the EC2 console, you can select the instance type icon. And basically, it will give you the possibility to navigate the different instances, select the different instances. And for all these instances, you will be able to see from a single page all the characteristics of the instances, like the number of cores, the amount of memory, the sustained clock speed, and so on. And of course, also the price. So you can make your choice, taking into account not only the performance, but also your badge. So this is just a screenshot, but if you click on the wheel, you will be able to customize this view and add multiple parameters that are important for your selection. Finally, please remember that one of the value of the cloud is that you don't really have to choose, in the sense that you can always experiment. So please feel free to try different things, to experiment until you found the right choice for you. Or feel free to contact us in case you want more information. I will share with you later a couple of links that can be useful. And also, most importantly, we continuously upgrade and refresh our selection of instances. So maybe today you are running on C5 instances, but tomorrow C6 instances will be available. And so it will be easier for you to reconfigure your parallel cluster to immediately jump to these new type of instances and start benefit from the new and improved price performance. Okay, so now let's come back to the demo and let's see how to configure parallel cluster for to take into account all the different instances that we have and all the different parameters we have seen previously. Okay, we are back. So I have prepared in advance a parallel cluster configuration file. This is what I have prepared to run an OpenFOAM demo. So we can read it together, this configuration file. That is very similar to the one that we have created before, but it's just more advanced. It contains more parameters. By the way, I will share with you a link at the end of this presentation, so you will be able to also to download this code, this example, and so you will be able to reproduce in your account what we are seeing here. So if you remember, the first thing we have selected is the AWS region. So you will find here in this configuration file. So if you want, you can edit it if you want to deploy the cluster on a different region. This is also very convenient. I mean, if your user base is distributed around the globe, you can easily copy this file, pass this file in an email, for example, and then each person can download his own cluster in the region that is closer to their user base. So you can select the region. Then there is the alias for the SSH connection, and then we jump to the cluster definition. That is probably the most important section. As you can see, the configuration is organized in several different sections. So in the cluster section, I have selected the key I want to use. So webinar key, once again, the scheduler, this example is Learn, and the instance type. So here you see a first difference in comparison to the previous one. So the previous one, I have selected T2 instances for the master instance type. In this case, I want a G4DN. Why? Well, because as you have seen in the previous slide, these are the instances powered by NVIDIA T4 GPUs. And in this demo, I would like to show you how to use DCV for remote visualization. DCV can also run on a CPU, but of course, the performance for graphic-intensive application will be much better if you run on a GPU. Then I selected the OS, in this case is Amazon Linux 2, and the VPC. That is the default is a link to the section that you will see later. There is the queue setting. So as you can see in this example, I have configured two different queues, the compute queues and the queue for the mesh queue. These are just labeled. We'll see later how to configure these labels. Then I also have requested DCV settings, so default, and FSX and EFS. So let's see how these are configured. So let's scroll down a little bit. So the first section we encounter is EFS. So here I'm asking parallel cluster to automatically mount my EFS. And this is very convenient if you want to share the binaries of the application across multiple installations. Of course, you have to replace the XXX with the ID of your EFS. The second section is for FSX. So in this case, I'm asking not to reuse an existing FSX, but to create a new one for me. And I am passing all the parameters that I want for my FSX. So the mount point, the storage capacity, that is 1.2 terabyte, the type of deployment, the storage type, and so on. We don't need now to dive deeper into the FSX parameters, but basically here you can include all the options and all the tunings of FSX to tune your Lastre file system. And then I also have asked to enable DCV on the master node. The VPC section, here I specify the VPC ID and the subnet that I want to use. So in your case, you will replace these with your ID. And now let's jump into the queue section. So as I said before, I have two queues. The first one is compute. This is the one I want to use to run the MPI jobs. So as you can see, I have enabled EFA. I have enable EFA equals true, so that parallel cluster will automatically enable the low latency network for me. I've asked a placement group dynamic, so that means that all the instances will be automatically deployed in the same placement group. This is also very important so that you can reduce the latency across the nodes. And I have also asked parallel cluster to disable the hyper threading for me. As you know, in AWS, most of the EC2 instances have the hyper threading automatically turned on. So if you want to disable hyper threading, in some cases this can improve the performance. You can use this parameter with parallel cluster. Then I select the compute type. This example I have on demand, but if you want, you can just type spot if you prefer to use spot instances. And then there is a link to the resource settings that in this case is called default, where you specify the instance type. You can have multiple instance type on a queue. In this example, I have just one, that is the C5N Actinix large. As you can see, I am selecting an instances with the N that are the one that can benefit from EFA. And I have selected a mix count of 0 and a max count of 100. So I will be able to scale these type of instances between 0 and 100 instances. The second queue is the queue that I want to use for the mesh. So I know that in this case, I don't really need a low latency network, so I haven't not configured EFA. I have disabled EFA. And I have configured a different instance type, that is the M524X large, and also the quantity is a little bit smaller, between 0 and 10 computing nodes. So in this example, I have used on demand, but as I said before, you can always switch to spot just by changing the compute type. Okay, so my configuration file is ready. Now I can create a new cluster. The command is the same you have seen before, but now I will specify, using the C flag, this new configuration file that I have just configured. So with this command, you will start creating your cluster. Okay, so we have seen how to configure, how to have an advanced configuration in parallel cluster. I have started the creation of my cluster to run OpenFOAM. Now let's see how to run your first job. Okay, my cluster is ready. I logged into the cluster and I have prepared a Slurm script to submit my job. So here you can specify the job name, the number of cores that you want to use, the compute, the partition that is the name of the queue, and the constraint. So the constraint is basically the instance type that you want to use. As you have seen before, you can have multiple instance type within the same queue. So then when you submit your job, you have to select which one you want to use with the constraint parameter. Then the rest of the script is basically a standard OpenFOAM submit. So I create my Scratch area. Of course, I want to create it on FSX. I copy the motorbike demo, and then I prepare the MPI run. I use MPI run to run the MPI job. So once you have prepared your script, we can control with the SQ the sides of the queue. As you can see, at the moment I have 0 nodes, so my queue is empty. And then using the sbatch command, you can submit your first job. So in this example, it's job number 5 because I already have done some tests in advance. So now with SQ, you can see that I have 3 nodes, and the status of these 3 compute nodes is CF. It means that basically Slurm is provisioning these 3 nodes for me. Why 3 nodes? Well, if you have seen before in the number of core, I have selected 108 cores. So Parallel Cluster will automatically do the math for me because he knows that C5N, so the instance type I've selected, these are powered by 36 physical core. Remember, I have disabled the hyperthreading. And so 108 cores divided by 36 equals 3. So it needs to start 3 instances to run my job. So now we have to wait 1 minute to start the instances. So if we go back to the console, you will see that now we have 3 compute instances that are initializing. These are 3 C5N instances, as I have requested. We can watch the SQ command to control the status of the job. So we are still waiting for the instances, but now we should move to the running phase. Okay, it's running now. So the instances are ready. We can come back to the console. You will see that they are no longer initializing, but they are ready to run, and the job is running on these 3 nodes. Okay, so now we have to wait a little bit the job to complete, but I think we can probably skip this section. We can have a look at the log files that are generated by the job. So the first one is the Slurm log file. That's just telling me the Scratch directory that I'm using. And then if we go to the Scratch directory, so on the Lustre file system, we can have a look at the OpenFOAM logs. Okay, of course, in these cases, I have installed in advance OpenFOAM, but you can use your own preferred application. In our blog post, we have published a benchmark for Fluent, for StarCCM, for GROMACS. We have a number of instructions for different types of HPC applications. Okay, so let's have a look at the queue, what the job is doing. Still running. I think we can accelerate a little bit. Okay, here we go. So the job is now done. Parallel Cluster will automatically terminate the instances for me, and I can control the output in the log files. Okay, so now let's see what you can do in order to visualize the results. So we can come back to the Parallel Cluster command line, and we can use the DCV connect command. Once again, you have to specify the cluster that you want to connect to. So this is my OpenFOAM cluster, and you have also to specify the SSH key that you want to use to connect. You have to specify the -key flag. Then, as an output, the Parallel Cluster client will give you an URL that you can cut and paste in your browser, and then you will be basically establish a DCV connection between the browser that is running on your local laptop and the DCV server that is running on the head node on AWS. And as you can see here, you have a full Linux desktop. And so you can install and use all the application that you have installed in advance. And obviously, the file system that you have configured before is also automatically mounted on the head node. So in this case, I can start, for example, ParaView, and then visualize the output of the simulation that I have run before. Okay, here we go. So this is the output of the simulation, and you can use all the the ParaView commands to analyze your results and then eventually submit another another job. Okay, we are done. Let's recap what we have seen today. So we have installed the AWS Parallel Cluster command line. We have configured the HPC cluster. We have submitted our first job on AWS. And then we have visualized the results remotely using NiceDCV. As I said before, at this link you can find more information. For example, we have our HPC Lens, the well-architected framework for high-performance computing. This is our reference architecture, but we also have blog posts and web pages where you can dive deeper on all the services that I've mentioned today. So Parallel Cluster, Patch, EFA, and FSx for Lastre. All the code that I have used is taken from a workshop that we have in place. For example, we have this workshop on OpenFOAM, so you can go on this URL and download all the code that I've used today. But we also have other examples in the HPC workshop page. If you need more information, our main page is aws.com/HPC, and from this page you can click on the button "Contact the AWS HPC team." So if you want more information, you can find many white papers, webinar, blog posts from our homepage, and you will also find a link to all the services that I mentioned before. And if you want to contact us, you can just have to fill the form that is behind the contact button. Okay, so thank you very much for your time. I think that we can now move on to the Q&A section. Thank you.